The story of the end of everything must begin, paradoxically, at the very beginning, around 13.8 billion years ago. All of reality, space, time, energy, and matter was compressed into an unfathomably small point. In a moment we call the Big Bang, this singularity expanded, not into space, but as space itself. There was no outside from which to watch it happen. Time itself was born in that instant. Before the Big Bang, our understanding collapses. There was no before, not in any conventional sense, because there was no time to measure. In those first fractions of a second, the universe inflated at an unimaginable speed, far faster than the speed of light. This wasn't an explosion, but a stretching of space itself. Tiny quantum fluctuations were pulled apart, seeding the structure of everything that would come. From chaos came order. As the universe cooled, particles formed, protons, neutrons, electrons, all the basic ingredients of matter emerged in the first few minutes. Hydrogen and helium dominated, eventually pulled together by gravity into stars, galaxies, and clusters. These first stars lived fast and died young, exploding in cataclysms that scattered heavier elements, carbon, oxygen, iron, into space. From the remnants of stars, new generations were born. Planetary systems emerged. Somewhere, on one small blue planet in an unremarkable corner of an average galaxy, life sparked. But all of that, every planet, every galaxy, every black hole, it all stems from that one singular beginning. And if there was a beginning, there must be an end. To understand the death of the universe, we must understand its origin, because the clues to its final fate lie in how it began. The universe has been expanding ever since the Big Bang. For decades, astronomers wondered whether that expansion would continue forever or slow down, possibly reversing into a collapse. But in the late 1990s, something unexpected was discovered. The expansion is not slowing. It's accelerating. This finding changed everything. It suggested that a mysterious force, dark energy, is pushing the fabric of space apart faster and faster. Dark energy doesn't behave like matter. We can't see it, touch it, or contain it, but its fingerprints are visible across the cosmos. Galaxies are racing away from each other faster than expected. The further away they are, the faster they seem to go. What does that mean for the end? It depends. The universe could expand forever, growing colder and darker as stars burn out and matter decays. Or dark energy could grow stronger, ripping everything apart in a cosmic climax. Or maybe, just maybe, quantum instability could suddenly erase the very laws that govern us, wiping the slate clean in a flash. These are the possibilities we'll explore, but we must keep in mind, they all begin with that single flash of light at the beginning of time. The Big Bang wasn't just a moment, it was a direction. It set everything in motion, gave us the arrow of time, and marked the birth of entropy. Entropy, the tendency of systems to move toward disorder, will become a central character in this journey. Because in the end, it may not be a violent cataclysm that finishes the universe, but a slow, inevitable fading into stillness. The universe didn't begin in silence. It was born in a furious storm of creation, but it may end in silence so complete that even time itself loses meaning. So before we dive into the theories of how the universe might end, we need to hold on to this truth. We are living in the aftermath of a miracle of order carved from chaos, of complexity rising from simplicity. Every atom in our bodies was forged in the heart of a dying star, and every breath we take is a continuation of that 13.8 billion-year-old story. But like all stories, this one has an ending. And to find it, we'll need to follow the universe through its life cycle, from its radiant youth to its dark and silent future. The end of everything begins with understanding how it all began. As the universe emerged from its fiery birth, it began a slow but majestic transformation. In the beginning, it was a hot, dense sea of particles, radiation and energy, all swirling in a chaotic dance. But over millions and then billions of years, something extraordinary happened. Gravity, the gentle but relentless force, began to weave its invisible threads across the cosmos, pulling matter together into clouds, stars, and galaxies. The universe was no longer a formless expanse, it became a vast cosmic tapestry of structure and order. Stars were the universe's first shining beacons. Born in enormous clouds of gas and dust, they ignited through nuclear fusion, turning hydrogen into helium and releasing vast amounts of energy in the process. Each star was a furnace, a place where the elements that would one day form planets, oceans, and life were forged. The stars were not eternal, however, their lives were marked by cycles of birth, evolution, and eventual death. Some stars, much more massive than our Sun, lived fast and died violently, exploding as supernovae and scattering their enriched guts across space. These cosmic explosions seeded the universe with heavier elements like carbon and iron, the building blocks of planets and biology. Over time, galaxies formed enormous collections of stars, gas, dust, and dark matter, held together by gravity. Some were spiral, like our own Milky Way, with elegant arms winding outward. Others were elliptical or irregular, shaped by collisions and the chaotic nature of cosmic evolution. Within these galaxies, stars continued their life cycles, and planetary systems emerged around many of them. The delicate balance of forces allowed the formation of stable worlds, where conditions might someday allow life to flourish. Yet even as stars and galaxies shone brightly, the universe continued to expand. This expansion stretched the fabric of space-time itself, pulling galaxies apart. But it wasn't just a simple spreading out. The universe's growth influenced its fate, and the story of its life cycle was deeply tied to how this expansion played out. As the eons passed, stars gradually used up their fuel. Massive stars lived only millions of years, while smaller stars like our Sun could burn steadily for billions. But inevitably, all stars face an end. Some collapse into dense remnants called neutron stars or black holes. Others fade away as white dwarfs. The birth rate of new stars slowed as the reservoirs of gas and dust were exhausted or heated beyond collapse. Without fresh fuel, the universe began a slow decline in star formation, signaling the approach of a quieter era. This transition marks the universe's middle age, a time when the cosmic fireworks give way to a more subdued but no less profound evolution. Galaxies grow dimmer, and the brilliant lights that once dominated the cosmos begin to flicker and fade. Yet, this process takes place on timescales so vast they defy human imagination. We're talking about tens of billions, even trillions of years stretching ahead. But the universe's story isn't just about matter and energy, it's also about entropy, a measure of disorder. From the moment of the Big Bang, entropy has been increasing. Systems tend to move from order to chaos, from energy available to energy spent. This relentless march toward disorder shapes the fate of everything. Stars burn their fuel, planets cool, black holes slowly evaporate. Over incomprehensible time, the universe approaches a state where no more work can be done. No more energy can be harnessed to sustain change or life. Our existence, brief as it is a fleeting sparkle in this cosmic timeline. Yet, it is precisely because the universe has aged so much that we can look back and understand its life cycle. Observing distant galaxies, we see light that began traveling when the universe was young, giving us a window into the past. This cosmic archaeology reveals the universe's growth, the formation of structure, and the slow fade toward its future. While this chapter in the universe's story is filled with light and life, it also foreshadows the eventual decline. The dance of creation and destruction continues, but creation slows and destruction becomes dominant. Stars will cease to form, galaxies will drift apart, and the universe will become colder and darker. The life cycle of the cosmos is one of beauty but also of inevitable decay, a reminder that all things, even the vastest of all, are subject to time. As we contemplate this vast cosmic life cycle, it's humbling to recognize our place within it. We are made of star stuff, temporary residents of a universe that continues to evolve long after we are gone. The universe's story is one of transformation, from hot beginnings to a slow cooling, a journey marked by the rise and fall of light. Understanding this journey is essential before we can fully grasp how it might one day end. The story of everything is a cycle of birth, life, and eventual death, played out on the grandest stage imaginable. As we move deeper into the cosmic timeline, we begin to see the shadows lengthen. The universe, once blazing with the light of countless young stars, is now entering what cosmologists call the Stelliferous Era, an age dominated by stars, but slowly tipping into decline. We're currently living in this era, surrounded by billions of galaxies, each filled with billions of stars. But what many don't realize is that we are already past the peak. Star formation in the universe reached its maximum roughly 10 billion years ago. Since then, the rate at which stars are born has been steadily decreasing. Galaxies have used up much of their raw material, hydrogen gas, that fuels star birth. What lies ahead is a future in which the cosmos gradually runs out of new light. Our sun, like all stars, has a finite lifetime. It's halfway through its life cycle, and will eventually swell into a red giant, engulfing the inner planets and ending life on Earth. It will then shed its outer layers and leave behind a white dwarf, a dense, slowly cooling ember of its former self. Multiply this by hundreds of billions, and you get a universe slowly filling with these fading corpses of stars. White dwarfs will persist for trillions of years, growing ever dimmer until they become black dwarfs, cold, dark remnants with no light left to give. Yet even these aren't the final word. In the far future, far beyond the comprehension of human history or civilization, the Stelliferous Era will end. Galaxies will grow dark as the last stars flicker out. New star formation will cease entirely. The night sky, now so vibrant with pinpricks of light, will become a void. And in that silence, only the remnants remain. Brown dwarfs, white dwarfs, neutron stars, and black holes, stellar leftovers that no longer shine. This era, where remnants dominate, is the beginning of the degenerate era. But before we get there, something else must be considered: the continued expansion of space itself. In the 1990s, scientists discovered that the expansion of the universe isn't just continuing, it's accelerating. Galaxies aren't just drifting apart, they're speeding away from each other. And they're not doing this because they're moving through space, but because space itself is stretching. This acceleration is powered by something we call dark energy, a mysterious force that seems to be embedded in the fabric of the universe. It makes up nearly 70% of all the energy in the cosmos, yet we know almost nothing about it. As space stretches faster and faster, galaxies outside our local group will eventually slip beyond our observable horizon. In about 100 billion years, distant galaxies will disappear from view entirely. Future observers, if any still exist, may believe they are alone in the cosmos, unaware of the grand structure that once connected all galaxies in a vast cosmic web. The night sky will become emptier, not because stars have vanished, but because the universe has outpaced the speed at which light can reach us. This isolation has profound implications. As the universe ages, not only does it become darker, it becomes lonelier. Communication between distant civilizations becomes impossible. Cosmic archaeology, the study of the past through light from distant galaxies, becomes forever limited. It's as if the universe is slowly pulling the curtains closed, one galaxy at a time. Meanwhile, black holes grow in influence. Throughout the Stelliferous Era, massive stars collapse, yet even they will not last forever. Thanks to Stephen Hawking's revolutionary theory, we know that black holes aren't completely black. They emit a faint glow of radiation, now known as Hawking radiation. This radiation causes black holes to slowly lose mass and evaporate. For massive black holes, this process takes unimaginable lengths of time, on the order of 10 years or more. But eventually, even the largest black holes will shrink, fade, and vanish into nothingness, leaving behind only faint ripples in the cosmic sea. By this point, the universe will be unrecognizable. No stars, no galaxies, no black holes, just a vast cold void scattered with subatomic particles and decaying debris. Protons themselves may decay, although we haven't yet confirmed this experimentally. If they do, then even the matter that once formed planets, people, and stars will disintegrate into radiation. Only the faintest, most fundamental forms of energy will persist. This long, slow descent into stillness is the theory of heat death, also known as the Big Freeze. It's not an explosive end, but a fading one. Entropy will reach its maximum. No gradients of energy will remain to power processes. No complexity, no movement, no life. The universe will be in perfect thermodynamic equilibrium, a state in which nothing ever happens again. This is the slow death of all potential. And yet, it is in this stillness, this silence, that we grasp the full scale of what the universe is. From the blazing birth of the Big Bang to the final whisper of fading particles, the universe's story is not one of despair, but of majestic transience. We are part of this story, a brief spark in a vast symphony that stretches across unimaginable time. The third chapter of the universe's end reminds us that all things change, that even the stars must rest, and that the universe, like life itself, is beautiful because it is fleeting. As the last stars fade and the galaxies fall silent, the universe enters what physicists call the degenerate era, a period of darkness where light becomes a memory and energy becomes scarce. This age is dominated not by shining suns or swirling galaxies, but by the remnants they've left behind: white dwarfs, neutron stars, brown dwarfs, and above all, black holes. The cosmos is no longer a place of creation, but of slow, inevitable decay. The fiery drama of stellar life gives way to a cold stillness, stretching across unimaginable spans of time. Without fusion to power new stars and without enough dense gas clouds to reignite stellar birth, the cosmos becomes a graveyard of faded embers. Brown dwarfs, failed stars that never had enough mass to ignite, drift endlessly. White dwarfs, once the hot cores of dead stars, continue to cool until they become black dwarfs, invisible and frozen. Neutron stars, the collapsed remains of massive stars, persist as ultra-dense spheres, city-sized yet containing more mass than our sun. Though some may continue to collide, producing flashes of energy, such events become increasingly rare in the thinning fabric of space. Black holes, once the silent guardians of galactic centers, now roam the cosmos like ancient giants. By this point, they've consumed much of the matter around them. Entire star systems, planets, even light itself have been swallowed. Gravity is their only voice, a quiet pull in an otherwise mute universe. And though they seem eternal, even black holes are not immune to time. According to Hawking's groundbreaking theory, they slowly radiate energy, a process now incredibly relevant. In a universe with no new stars, black holes begin their own quiet evaporation. The larger they are, the slower they fade, but fade they do. This process, known as Hawking radiation, will eventually spell the end of even the most massive black holes. As they radiate, they shrink, and as they shrink, they radiate faster. It's a cosmic irony that the darkest objects in the universe are fated to vanish in a final blaze of ghostly particles. The last black holes may persist for 10⁻⁻⁻ years or longer, a number so vast it shatters the boundaries of human imagination. And when the final black hole vanishes into quantum sparks, the universe will be left in absolute darkness. But the degenerate era offers one more haunting question: what happens to matter itself? Some theories suggest that protons, the building blocks of atoms, may not be truly stable. If protons decay, and current models allow for this possibility, then even the atomic structure of matter will eventually collapse. After another vast span of time, perhaps 10⁻⁻⁻ years, every atom in the universe will decay into subatomic particles, and then into radiation. In this scenario, even the most stable objects, the black dwarfs, the neutron stars, will dissolve. There will be no solid matter left, just a sparse bath of photons, neutrinos, and other elementary particles, racing through an almost entirely empty void. In this final stage of the degenerate era, what remains is governed by quantum mechanics, entropy, and chance. The universe has become so large and so cold that even basic particle interactions are rare. With no new sources of energy, and no gravitationally bound systems remaining, even gravity becomes irrelevant at large scales. The cosmic expansion driven by dark energy, continues to accelerate, stretching space so vastly that any remaining particles may never meet another again. The universe becomes functionally static, empty, timeless, quiet. What's particularly striking is the loneliness of this era. Every trace of complexity, stars, planets, life, thought has dissolved. No civilizations remain to observe the stars, no eyes left to look up and wonder. Time itself loses meaning when nothing changes, when no processes occur. In this frozen moment, stretched infinitely forward, the universe reaches maximum entropy. In thermodynamic terms, this is the heat death of the universe, not because it is hot, but because all energy has been evenly distributed. There are no gradients, no reactions, no structure. It is the ultimate equilibrium, and it is utterly still. And yet, within this silence, within the seeming death of everything, there's a strange kind of poetry. The degenerate era isn't just about decay, it's about endurance. Objects and forces that emerged billions of years ago have lingered across aeons, long after the conditions that created them vanished. Black dwarfs and black holes survived far beyond the lives of galaxies. Particles born in the early universe still race through the void. In a way, the universe has become the memory of its own existence. Nothing new can be created, but everything that remains is a trace of what once was. Some speculative theories even suggest that something unexpected could happen in this desolate stage. Tiny quantum fluctuations, for example, might someday create new universes, a process known as false vacuum decay or bubble nucleation. These are only theories and highly uncertain, but they serve as reminders that even in the bleakest timescales, we still search for possibilities. Perhaps entropy, the great unraveler, also sows the seeds of renewal in ways we don't yet understand. But for now, the fourth chapter in the death of everything is one of inevitability. It's a slow, patient descent into silence. From the golden age of star birth to the slow cooling of stellar remnants, from the quiet reign of black holes to the possible decay of protons, this is the great fading. The degenerate era teaches us that even the grandest systems, galaxies, stars, matter itself, are impermanent. And it humbles us with the scale of time, for as we live our fleeting human lives, the universe marches ever onward toward its still, cold end. And so we arrive at the chapter where not just stars, galaxies, and matter vanish, but time itself begins to lose its meaning. This is the black hole era, a period stretching across unimaginably vast timescales, where black holes, those dense, inescapable wells of gravity, are the final sentinels of structure in the universe. Everything else has faded or decayed. The stars are gone. The atoms are gone. Even protons, the core of matter, have likely disintegrated into energy. What remains are black holes drifting through a dark and expanding cosmos, each one a relic of a universe that once teemed with light and life. These black holes vary in size and age. Some are stellar mass black holes formed from the collapse of individual stars. Others are supermassive, born in the hearts of galaxies, weighing millions or billions of solar masses. Though their formation took seconds or minutes, their end takes eons far beyond any scale our human minds can easily grasp. But their fate is not to last forever. Hawking radiation, a quantum mechanical process first theorized in the 1970s, ensures that even the most massive black hole cannot escape the ticking clock of entropy. Slowly, very slowly, they begin to evaporate. This evaporation isn't dramatic at first. For billions upon billions of years, a black hole might emit only the tiniest trickle of particles, photons, neutrinos, and other lightweight radiation. The larger the black hole, the slower this process. For a black hole the mass of our Sun, the evaporation process takes n-half-its years. For supermassive black holes, it's even longer, up to 10-half-its years or more. But time in the black hole era is no longer a barrier. The universe now exists on a canvas stretched so thin by expansion and so long by time that numbers like 10 cool the first are as natural to it as seconds are to us. Eventually, as each black hole loses mass, the rate of radiation increases. A once silent monolith begins to glow, faintly at first, then more intensely as it shrinks. In its final stages, A black hole radiates rapidly, heating up and spewing energy into the darkness. Then, in the blink of a moment, relative to its eternal lifespan, it vanishes in a final flash of energy. Not an explosion, not a supernova, just a quiet last breath of the universe's last structure. When the last black hole evaporates, the universe is left with almost nothing but low-energy photons, neutrinos, and possibly dark matter particles drifting in an unimaginably vast expanse. This moment, when the final black hole dies, is one of profound cosmic silence. No gravity wells remain. No sources of light or complexity exist. The last dance of matter is over. This is not just the death of things. This is the death of the possibility of things. Without gradients of energy, without asymmetry, without imbalance, nothing can change. And in the language of physics, change is time. So in a very real sense, time itself stops having any relevance. The clock of the universe no longer ticks. It drifts endlessly in a sea of sameness. Yet, even in this final silence, we cannot help but wonder, is this truly the end? Some physicists propose that in this desolate sea of radiation, rare events could still occur. Perhaps random quantum fluctuations could momentarily create particles or even atoms. Perhaps in some far future moment, a strange accident of chance could produce a structure, a brain, a planet, a replica of the universe itself. These ideas are highly speculative and deeply controversial, known in theoretical circles as Boltzmann brains or vacuum fluctuations. But they underscore a lingering truth. Even when the universe has died, our imagination hasn't. Another possibility looms, both fascinating and terrifying, the concept of false vacuum decay. If the universe exists in a metastable state, a kind of temporary balance, it could at any moment transition to a more stable vacuum. This would create a bubble of true vacuum expanding at the speed of light, rewriting the laws of physics as it goes. If this were to occur, it wouldn't just end our universe as we know it, it would remake the very structure of reality, erasing all current particles, forces, and even dimensions. We wouldn't see it coming. There would be no warning. One moment the universe exists, the next it doesn't. But barring such dramatic reboots, the black hole era ends with finality. With no energy gradients left, with all entropy maximized, the universe becomes a thin fog of cold, low-energy radiation stretching into infinity. The age of galaxies, stars, and life has long passed. Complexity has lost the battle to entropy. And now space itself is a shadow, featureless, lifeless, eternal. This stage in the universe's death is haunting, not because of violence or sudden collapse, but because of the slow, relentless inevitability of it. Black holes, once seen as the most fearsome objects in the cosmos, go out not with a roar but a whisper. They outlive everything, yet they too are temporary. This erasure isn't just physical, it's informational. According to some interpretations of thermodynamics, as entropy reaches its maximum, even the memory of the universe's existence fades. Nothing can hold or recall what once was. The past is lost, not just to minds, but to the fabric of reality itself. And so the black hole era passes into legend, not because anyone remains to remember it, but because we in this brief bright moment of the universe's youth have dared to imagine it. We have charted the future not to embrace despair, but to better understand our place in this incredible fleeting cosmos. And though we may vanish, the questions we ask now echo into the quiet that follows.
By the time we reach this stage in the journey, the era following the death of all black holes, we've moved into a time so vast, so stretched beyond conventional imagination, that human language begins to break down. This is the dark era. No stars, no galaxies, no black holes, no atoms, only particles, ghostly, cold, and scattered thinly across a universe that has expanded beyond what any early observer could have ever foreseen. The universe hasn't just aged, it has emptied itself, diluted into near nothingness. The canvas remains, but the paint has faded.
It is in this long, quiet chapter that we explore what happens when everything, quite literally, is gone. In this time beyond time, the universe is mostly photons and neutrinos, particles that barely interact and travel in straight lines forever. Temperatures have plummeted to near absolute zero, asymptotically approaching it, but never quite reaching. The concept of temperature, energy, and structure loses relevance. The cosmos has reached a state of near-perfect thermodynamic equilibrium. This means no more change, no more usable energy, and no more potential for anything complex to arise or evolve. It's not just the end of matter, but the end of possibility itself. What remains is entropy, a universe fully entropic, meaning it's reached the maximum disorder possible. But this disorder isn't chaos in the sense of motion or randomness. It is a smooth, quiet uniformity. Ironically, in the earliest seconds after the Big Bang, the universe was also in a kind of high entropy state. But back then, entropy meant intense heat and density, energy waiting to spread. Now, entropy means the opposite, utter stillness, where everything has already spread out, thinned, and died. There is no light because there is nothing left to emit it. Photons may still fly across space, but they are so cold and so widely scattered that even if they encountered something, there would be nothing left to interact with them. It's not darkness as we know it, it's a lack of light that can no longer be perceived or matter that can reflect it. It is the black stillness of an empty infinity. If a human could somehow survive here, they would see absolutely nothing, no stars, no cosmic background glow, just the eternal absence of contrast. But some theories suggest there's more to consider. Some physicists propose that even in this dark, dead state, quantum mechanics doesn't sleep. The vacuum of space, even when cold and nearly featureless, may still flicker with temporary bursts of virtual particles, pairs of particles that pop in and out of existence. This is not the same as the rich particle field of the early universe. These are transient ghosts, microscopic blips that leave no lasting structure. But it suggests that even in death, the universe might never be truly still. Then there is the tantalizing and controversial concept of Poincaré recurrence. According to this idea, in a closed system with a finite amount of energy and matter, given enough time, the system will eventually return to a state very close to its original condition. It's like saying that if you shuffle a deck of cards enough times, perhaps trillions upon trillions of times, it will eventually return to its starting order. For the universe, this implies that, given a long enough timeline, far, far beyond even 10 circumflex 1,000 years, it could randomly fluctuate back into a state resembling the Big Bang. A new universe could, theoretically, emerge from nothing, simply because of the infinite patience of time and probability. But this isn't a hopeful rebirth in the traditional sense. Most fluctuations in a high-entropy universe would result in something far less interesting than a universe, like a random quantum blip or a momentary flicker of radiation. Only once in an unimaginable span might something universe-like arise. And the idea is deeply unsettling because it implies that such a rebirth wouldn't carry any memory or meaning from our own. It would be, in every way, a separate, disconnected occurrence, a new roll of the cosmic dice. This brings us to the haunting thought experiment of Boltzmann brains, named after physicist Ludwig Boltzmann. The idea is that in a universe governed by random quantum fluctuations, it's statistically more likely for a disembodied consciousness to momentarily flicker into existence than for an entire universe to form again. This hypothetical brain might have temporary memories, thoughts, and self-awareness before blinking back out of existence. The thought is bizarre, even comical, but it's also philosophically disturbing. It challenges our understanding of reality. How can we be sure that we aren't such a temporary fluctuation ourselves? And yet, for all this speculation, the most accepted and probable future of the universe is simply more of the same. More expansion, more cooling, more stillness. The cosmic horizon, the maximum distance from which information or light can reach us, continues to grow. Eventually, even the few remaining photons and particles will be stretched so far apart that they become essentially unobservable.
The universe becomes isolated on every scale. Not just lonely, but disconnected. Every possible interaction, every potential for causality, fades. As time moves forward, even decay itself becomes irrelevant. Everything decayed long ago. There is no center, no edge, no frame of reference. There is only a fabric of space-time with no purpose, no observer, and no end in the traditional sense. It is an infinite extension of a process that has already played out. Death here is not an event, it is a condition, an eternal stasis, a kind of cold immortality. But within this bleakness lies the deepest questions of philosophy and science. If the universe ends in nothing, does that mean its entire journey, from the Big Bang to the rise of galaxies to the spark of conscious thought, was meaningless? Or does it mean that the meaning is found not in how the universe ends, but in how it lived? After all, the very fact that we can contemplate the heat death of the universe, from our tiny planet in this brief cosmic moment, is something extraordinary. The universe, through us, is witnessing its own story. And so this chapter doesn't close with a dramatic collapse or an explosive finale. It ends with a whisper, stretched over endless eons, in which the universe ceases to change, and therefore, in a real sense ceases to be. Time becomes meaningless, physics becomes quiet, and yet, in that silence, we are left with the ultimate reflection of what it means to exist in a universe that had a beginning flourished with complexity, and then slowly returned to simplicity. The universe dies, not with violence, but with silence. And in that silence, the story of everything comes to a close. Beautiful, haunting, and profoundly humbling. Even after the universe has faded into stillness, we are left with one persistent, mind-bending question: is this truly the end? Or could something come after the end? This is where our story shifts from cosmology to speculation, from observable physics to the fringes of what we can even imagine. In this chapter, we dive into the strange and beautiful possibilities that go beyond our current understanding, alternate endings, multiverses, and cyclic universes that may hint at rebirths in the ashes of cosmic death. The idea that our universe is the only one has been challenged for decades. The multiverse theory proposes that our universe is just one bubble in a vast sea of universes, each with its own laws of physics, its own beginnings, and its own endings. According to some models of inflation, the incredibly rapid expansion of space in the first fraction of a second after the Big Bang, this inflation doesn't stop everywhere at once. Instead, while it ends in some regions, creating universes like ours, it continues in others. This process, called eternal inflation, could be generating an infinite number of universes, each disconnected from the rest, expanding in their own isolated ways. In this framework, the end of our universe becomes less of a final chapter and more like the closing of a single book in an endless library. If eternal inflation is real, then even as our universe slips into heat death or fades into entropy, countless others could be born, live out their lives, and die, again and again. And perhaps some of them harbor life, structure, intelligence, echoes of what we once were. But what if our universe doesn't just fade away, but cycles? Some theories propose that the universe may not end permanently, but could be reborn. This brings us to the idea of a cyclic universe, a cosmos that expands, collapses, and expands again forever. The most famous version of this is the Big Crunch, where gravity eventually overcomes the expansion of the universe, pulling everything back together into an incredibly dense state, a mirror of the Big Bang. After this collapse, another Big Bang could ignite, starting the process all over again. This cosmic heartbeat could repeat eternally, each universe giving rise to the next in an endless dance of creation and destruction. However, current observations make the Big Crunch less likely. The universe's expansion isn't slowing down, it's accelerating, driven by dark energy. Still, modified cyclic models try to reconcile this by suggesting that dark energy itself might be unstable. Perhaps, in the far future, dark energy could change its nature or even reverse, pulling the universe back inward. These ideas remain theoretical, but they offer a deeply poetic notion that every end is simply a preparation for another beginning. Other variants of the cyclic universe don't rely on collapse at all.
Instead, they propose that time itself is cyclic, even if the universe keeps expanding. In this view, the end of time and the beginning of time are the same point. Like the hands of a clock returning to midnight, the universe could reboot not in space, but in time. When entropy reaches its maximum and everything stops evolving, a kind of reset may occur, and the conditions of the Big Bang arise again. It's speculative, deeply mathematical, and incredibly difficult to prove, but it allows for a cosmos that is eternal, even in the face of death. One of the most fascinating and bizarre theories about the end is the concept of vacuum decay. In quantum field theory, our universe may not be in its most stable state. Instead, it could be in what's called a false vacuum, a kind of temporary energy state that looks stable but isn't the lowest energy state possible. If that's true, then at any moment, the universe could experience a quantum event that triggers a transition to a more stable state. This would create a bubble of true vacuum that expands at the speed of light, annihilating everything in its path: atoms, stars, even the laws of physics as we know them. There would be no warning, no escape, no pain. It would simply be the end. But even this kind of end isn't a true end, because within that new vacuum, new physics might emerge, and with it, the potential for a completely different kind of universe. Each of these possibilities invites deep philosophical questions. If there are infinite universes, are there infinite versions of you? Does anything really die if everything can be born again elsewhere? What does it mean to exist in a multiverse where reality itself has no edge? These aren't questions science can answer easily. They live at the border between physics and philosophy, where data gives way to imagination, and equations collide with meaning. But there's another layer to this exploration, the human one. Why do we care so much about how the universe ends? Perhaps because it reflects something internal. The universe is in many ways a mirror. Its vastness humbles us. Its fragility reminds us of our own. To ask how the universe ends is, in part, to ask how we face our own end. Do we face it with fear? With curiosity? With hope? These questions take on a deeper resonance when we realize that we, as conscious beings, are the only known part of the universe capable of asking them. The concept of a multiverse also offers a strange kind of comfort. If other universes exist, then perhaps existence is bigger than any one tragedy, any one death, even the death of a universe. Perhaps somewhere, something will always exist to remember, to wonder, to dream. Or perhaps it's not about memory or survival at all. Perhaps the very act of being alive in a moment, even a fleeting one, is enough. In this light, the end of the universe becomes not a moment to mourn, but a reminder to cherish. We exist in a brief, miraculous sliver of time where the universe is alive, vibrant, and full of possibility. The stars shine now. We can see them. We can learn from them. We can wonder. That won't always be the case. And so, while we ponder the cold, quiet endings and the speculative rebirths, we are also invited to celebrate the now, the improbable, beautiful now. This chapter, then, is about what comes after the end, but it's also about why the end matters to us at all. It is a meditation not only on fate, but on meaning. Because in a universe that may one day forget us entirely, we still have the chance to think, to feel, to ask these questions. And maybe, just maybe, that is enough. In the boundless silence that follows the universe's final moments, whether through heat death, vacuum decay, or the final flicker of quantum instability, there's a strange beauty in contemplating what remains. But one aspect that lingers far beyond the dramatic endings is the legacy of information. In this chapter, we explore the role of information in the cosmos, how it shapes the universe, how it might survive its end, and whether consciousness and memory at the most fundamental level might be eternal in ways we don't yet understand. This is a story not just of atoms and gravity, but of patterns, data, and the very language of existence. Information in physics isn't just a human construct, it's deeply tied to how reality functions. The laws of thermodynamics, particularly the second law, are essentially laws of information. Entropy, at its core, is a measure of disorder, but more precisely, it's a measure of information loss or scrambling. As the universe evolves, entropy increases and structured information, like that found in stars, planets, life forms, gradually degrades. From a cosmic perspective, everything that happens is part of a continual shift from ordered states to disordered ones. But even as structures decay, the information they contain doesn't necessarily vanish, it transforms. This brings us to one of the most mind-bending concepts in modern theoretical physics, the idea that information can never be truly destroyed. It might be scrambled, it might be encoded in unrecognizable forms, but it persists. This principle became crucial during debates about black holes. When something falls into a black hole, where does the information about its structure go? For decades, it was assumed that it was lost forever, leading to the famous black hole information paradox. But more recent theories, including the holographic principle and work by physicists like Stephen Hawking and Leonard Susskind, suggest that the information is not lost. It is somehow preserved, perhaps on the event horizon or encoded in subtle quantum correlations. This has enormous implications. If information can never be destroyed, even the death of the universe might not be the end of everything. Somewhere, in the quantum fabric of space, the fingerprints of every star, every thought, every interaction may still exist. Think of it as a cosmic backup drive, not for the sake of reanimation, but for continuity.
The universe in this view is not just matter and energy, but also an evolving computation. A process that writes, stores, and transforms data. Some theorists extend this line of thinking even further, suggesting the universe itself is a kind of quantum computer. Every interaction, every quantum fluctuation, is part of a vast calculation that unfolds over time. This idea, sometimes associated with digital physics, implies that the cosmos could be governed by information rules, much like a simulation or a programmable system. While speculative, this concept merges the boundaries between physics and philosophy. If the universe is processing information, then it's possible that its ending isn't just a physical event, but a kind of logical conclusion, a final line of cosmic code. But what does this mean for consciousness, for memory, for identity? If information persists in some form, could the patterns of thought and mind be recoverable? Could consciousness be more than the arrangement of neurons and chemicals? Could it be an informational pattern that, under the right circumstances, might reemerge? This isn't about science fiction immortality or digital resurrection. It's a philosophical inquiry into whether the self, as an informational system, leaves echoes that matter in the grand equation. In our current understanding, human minds are temporary arrangements of matter, beautiful, fragile, and fleeting. But they are also nodes of complex information, processing sensory data, forming memories, and reflecting on their own existence. These patterns, encoded in the brain, expressed in language, recorded in books and data, become part of the universe's information stream. When we die, the pattern is broken. But was it erased, or merely scrambled? Now scale that up. Civilizations rise and fall, stars are born and extinguished. All of it contributes to the informational history of the universe. Even if no one remains to remember, even if the last light dims, the history still happened. It left a mark, and according to many interpretations of quantum mechanics and relativity, that mark is real. Events, once they occur, become fixed in space-time. Their information may be inaccessible, but it isn't undone. We must also consider the possibility that the universe may not be alone in carrying this information. Advanced civilizations, far beyond our current understanding, may one day find ways to encode themselves into the very substrate of space. Theoretical concepts like Boltzmann brains, self-replicating information clouds, or simulations encoded in the low-energy fabric of vacuum fluctuations are wild, but they push the question further: what if information is the only real permanence in a universe destined to end? The irony is that even as we talk about permanence, we must acknowledge the vast stretches of time ahead. After trillions upon trillions of years, even protons may decay. Black holes evaporate, photons redshift into oblivion, and the universe becomes so diffuse and so cold that nothing interacts meaningfully anymore. The stars are long gone, the galaxies are dark, no new structures arise, entropy is one. And yet, even then, there remains a kind of invisible ledger,
an imprint of what once was. It might be hidden in quantum fields or entangled in cosmic background noise. It may be irretrievable, but its existence, its ghostly presence, suggests that even the deadest of universes is not entirely empty. It is filled with echoes. So as we explore the 8th chapter of our journey toward the end, we find ourselves not in the presence of silence, but in the company of whispers. Information, the quiet record of all that ever occurred, may be the final survivor. It does not need to be conscious, readable, or meaningful. It simply is. And that may be enough. In the end, this chapter is not about avoiding death, but understanding it. The universe may die, but not forget. Its history, written in the language of physics, etched into the structure of space-time, will remain long after the lights go out. We are part of that story. And as long as information endures, so in some way, do we. As we move deeper into the final chapters of the universe's existence, the scale of time we must now consider stretches beyond human comprehension. Trillions of years have passed. The stars have gone dark. The black holes that once anchored galaxies have long since evaporated into a quiet hiss of Hawking radiation. What's left is an ocean of nothingness, vast, cold, and almost entirely empty. But there is still one more thing we must explore before we close the book on cosmic existence: the multiverse. The idea that our universe, as enormous and complex as it is, might be just one of many, perhaps even one of infinite others. And with this idea comes a deeply haunting possibility that the death of our universe might not be the end, but merely a transition into something else. Something stranger. The multiverse, as a scientific and philosophical concept, is not one idea but a family of ideas. Some versions come from inflation theory, suggesting that in the early moments of the Big Bang, different regions of space-time may have inflated at different rates, creating bubble universes with their own physical laws. Others arise from string theory, which allows for an immense number of possible configurations for fundamental particles and dimensions, each of which might define a separate universe with entirely different physics. Then there are interpretations of quantum mechanics, like the many worlds hypothesis, which claim that every quantum decision spawns a branching of reality, creating an infinite set of parallel universes for every possible outcome. The multiverse isn't just a theoretical playground. It's a serious proposition that challenges the uniqueness of our universe and the inevitability of its fate. If the multiverse is real, then the death of our universe might be localized, a singular event within a broader cosmic landscape. Our universe could be one room in an infinite mansion, and just because the light in our room is going out, doesn't mean the rest of the mansion isn't still bustling with activity. Other universes might be teeming with stars, galaxies, or entirely different forms of matter and energy. Some might be younger, just beginning their expansion. Others might be older, frozen in strange geometries or collapsing into singularities of their own. If so, then our universe is not a final act but one chapter in an infinite volume. But the multiverse doesn't just offer hope for continuity, it also deepens the mystery of meaning. If there are infinite universes with infinite variations of events, people, and outcomes, then what does it mean for anything to matter? Is our universe just one of many insignificant stories playing out across an unfeeling multiverse? Or is there something uniquely meaningful in the very act of existing, of observing, questioning, and understanding, even if we are just one flickering candle among countless others? Some physicists suggest that the multiverse may hold the key to resolving deep questions in cosmology. Why do the constants of nature seem so perfectly tuned for life? Why is the universe flat, homogeneous, and filled with the right ingredients to support complex structures? In a multiverse where every possible version of physics is realized somewhere, it's no surprise that we find ourselves in a universe that works. It's the only kind in which we could have evolved. This is the anthropic principle, controversial and often unsettling, because it suggests that our universe might not be special at all. It might simply be one of the rare ones where beings like us can ask these questions. And yet, even if we are just a statistical accident, there is a profound beauty in that. Out of the chaos of quantum fields, out of the randomness of cosmic inflation, arose a bubble of space that would one day give rise to stars, planets, and minds capable of contemplating the multiverse. We are the universe thinking about itself, not just this universe, but potentially every universe. The very act of asking these questions makes us participants in a cosmic dialogue we may never fully understand. Now let's return to the end, our universe in its dying moments. In some versions of multiverse theory, new universes can be born from the collapse or quantum decay of old ones. The death of our universe might spark the beginning of another. This new universe might bear no resemblance to ours. It could have different laws of physics, different dimensions, even a different structure of time, or it might be a close sibling, with only slight variations. Some suggest that black holes themselves may spawn baby universes in other dimensions, pinched off from our own space-time. If that's true, then even as our universe fades, it might be giving birth to new realities, like a cosmic seed dispersing across the multiversal landscape. The concept of eternal inflation paints a particularly stunning picture. In this model, the universe never stops expanding, not just our universe, but the broader space in which all universes exist. New pockets of inflation continually form and bud off, creating new universes forever. Our universe is just one bubble, among an infinite froth of other bubbles, endlessly spawning and evolving. The death of any one universe, then, is not an end. It's an ordinary event in an unending cosmic process. Still, even in a multiverse, we are faced with loneliness. These other universes, if they exist, are almost certainly inaccessible. The fabric of space-time in each is separate from the others, and no signal, no probe, no light can travel between them. This makes the multiverse not only scientifically elusive, but emotionally bittersweet. It may be real, but it offers no rescue. We cannot escape to another universe. We can only imagine them, yet the idea lingers, seductively. What if consciousness, or information, or some deeper principle of existence, can traverse the multiverse? What if death in this universe is not annihilation, but transition? These questions blur the boundary between physics and metaphysics, science and spirituality. We have no evidence, no equations that say this must be so. But in contemplating the multiverse, we open the door to infinite possibilities. Perhaps in one of them, this very moment is being played out again, in slightly different words. Perhaps you, watching this video, exist in countless versions, asking slightly different questions, reaching different conclusions. The multiverse, if real, is not just a physical extension, it's an existential one. As we close this chapter, the multiverse leaves us with a haunting duality. On one hand, it renders our universe small, even disposable, a single grain of sand on an infinite beach. On the other, it magnifies our significance by placing us within an endless symphony of existence. We are not alone. Not in the biological sense, but in the cosmological sense. Other universes may sing their own songs, shine their own stars, and one day face their own ends. But we are here now, in this one, aware of the possibility of all the rest. And that awareness may be the most extraordinary thing the multiverse has ever produced. The universe, in all its grandeur, mystery, and silence, is a story. A story that began with a sudden, incomprehensible explosion of energy in space, a singularity we call the Big Bang, and will eventually conclude in a whisper. But before the last echo fades, before the final wave of light stretches into invisibility, there's something deeply human we must confront. The ending of the universe is not just a cosmological question, it's a philosophical one, an emotional one. What does the death of the universe mean for us? For meaning itself. In this final chapter, we're not just exploring theoretical physics, but the soul of the question. How do we, as conscious beings living in a temporary cosmic moment, come to terms with the end of everything? Our universe is vast and old, but it is not eternal.
The entropy of the cosmos increases with every passing moment, pushing everything toward thermodynamic equilibrium, heat death, where no more work can be done, and all matter and energy are spread thin across an ever-expanding void. But long before that terminal state is reached, we must reckon with the intermediate silences.
the death of the stars, the evaporation of black holes, the collapse of structures that once defined galaxies. Over time, the fabric of reality will become sparse, and the cosmos will fall into a state of almost perfect stillness. No new light, no new life, just a sea of particles and radiation drifting further apart in infinite darkness. This ending, while predicted by the laws of physics, hits us in a uniquely existential place. Human beings have always sought to create meaning within stories, stories of beginnings, struggles, triumphs, and endings. We see this pattern in everything from mythology to science fiction to our own lives. The idea that our universe has a beginning and an end appeals to this narrative instinct. It makes us feel like part of a larger arc, something more coherent than chaos. But if the universe ends in cold silence, what does that arc amount to? What was it all for? Some scientists argue that meaning is a local phenomenon, not a cosmic one. Meaning arises wherever there is consciousness, wherever there is thought, feeling, or awareness. In this sense, meaning doesn't need to survive the universe. It needs only to exist within it, however briefly, like sparks in a dark room. Each moment of consciousness matters because it existed, not because it lasted. The universe, even if destined for oblivion, has already produced minds capable of understanding it, and that, in itself, is profound. In the brief window where complexity was possible, between the birth of the stars and the fading of the last light, life emerged, looked outward, and asked, why? But not all questions have answers, and not all endings offer closure. The final stages of the universe will not be dramatic. There will be no sudden collapse, no fiery apocalypse. Instead, it will be a long, slow fading. The stars will die quietly. The black holes will evaporate in virtual silence. And eventually, even subatomic particles may decay, leaving behind a universe of nothing but photons, neutrinos, and perhaps the faintest whispers of curvature in space. It's not the kind of ending our stories usually tell. It's not heroic, it's not tragic, it's simply inevitable. And yet, within that inevitability lies a strange kind of peace. For the first time, we understand enough about physics to trace the universe's probable path from beginning to end. We are not guessing in the dark, we are in a way reading the last pages of a book we only recently learned to open. To know that the universe will die is not to despair, but to appreciate the value of now. This moment, this breath, this thought, all of it exists within a brief chapter of cosmic history when stars still shine and thoughts can still be formed. We live in the golden age of existence, nestled between two eternities, the nothing before and the nothing after. Some people look to religion or philosophy to find solace in the face of cosmic death. Others find it in art, science, or connection. The truth is, how we cope with the universe's fate is as varied as humanity itself. But perhaps the most empowering perspective